Hi, everybody. I'd like to welcome you to our talk that's kind of this interesting hybrid of programming languages and science, which usually I would say the two often don't go together, but should more often. So Andreas Stefik is our speaker. He is from University of Nevada, Las Vegas. And I first met him when he was explaining statistics to a speaker at a conference. That was better than the way that the speaker could explain her own statistics. And that was pretty nice because Andreas is he feels very strongly about doing methodology properly. He's a very proponent of randomized controlled trials, especially when you're dealing with religious type questions, such as these things that will show up in programming language design. Lots of questions have been around since the beginning of programming languages that are unsettled still to this day. Andreas has been doing a lot of research into trying to figure out how to answer those questions in a scientific, data-driven way. So let me hand it off to Andreas to tell us all about that.
All right. Thanks for inviting me, Andy. I appreciate it, and I have the distinct impression I'm going to enjoy the dinner later as well. There's a home-cooked meal I've been promised, so I'm going to help, though. So as Andy said, my name is Andy Stefik. I'm a computer scientist by trade, but I've spent quite a lot of time with psychologists and people sort of in that vein. And I've spent the last few years especially being inspired by how other fields solve really big problems that the fields have. And so I kind of want to start with this story that was actually a very famous test that happened in the early 1800s. And so let me set the stage. There was this doctor, it's 1834, his name's Frederick Wilhelm von Hoven. And at the time, there were a variety of medical doctors and practitioners that were advancing this technique that they called homeopathic medicine, right? And that was the name. It started in the late 1700s by this guy named Samuel Hahnemann. And the idea was that was called like cures like, right? It was that if you have a condition that's bad and you have a substance like that, then maybe that will cure you, right? Is that a good idea? Well, it didn't hold up to the evidence. However, the problem is that there was no way at the time to really know for sure. So von Hoven was really skeptical that this might have been fraud, or at least he wrote a letter about it. This letter is very famous, called the von Hoven letter, right? It went to a local newspaper from a newspaper owner that was sort of anti-homeopathy, if you will. And it's very hard to read. At the time in 1834, you can get the letter, but the German letters aren't the letters that they are today. So even though my colleagues and I have expertise in German, it's very difficult to know exactly what he's saying without someone expertise in early 1800 Germanic languages. But words like charlatan and fraud are used quite regularly in this letter, right? And what this led to was actually a very famous test called the Nuremberg salt test. And it is widely regarded as the first what is called randomized controlled trial. And I'll get to this in a second. But here's the problem. The problem was at the time, the doctors didn't really know how to distinguish fact or belief or from fiction. Right? They weren't sure how to actually evaluate claims when someone made them about a medical practice or other things. So for example, von Hoven, when he put out his letter, he was challenged by homeopathists of the day, homeopathists that were getting money to practice, especially from the aristocracy. They were getting paid to do it, so they didn't want to give up their practice, of course, right? And they didn't trust each other. So von Hoven and his colleagues, which were also doctors, they were saying things like, well, we don't trust you, so if we give a treatment to patients, we don't necessarily trust them either. So we don't want them to know what they've been treated with. And the homeopathists, they're like, well, we don't trust you either. You're just going to cheat and have this fraudulent procedure, and then your methodology will show that we're bad, even though we're not. We're the good guys here. And at the same time, since neither one of them trusted each other, they crafted these procedures to sort of prevent fraud. And ironically, even though they had fraud prevention procedures in the test, people still committed fraud. And they were able to detect it using some sly techniques. It was early 1800s, right? So they weren't very good tests, but they were orders of magnitude better than what existed before. And because they didn't know whether homeopathy had an impact, they also had a non-homeopathic treatment. And there's all sorts of tests around the period. Some use things like bread pills, which is bread in a pill, or they used water, stuff like that. I know, shocking, huh? Right. But anyway, as you can probably imagine, the theory of light cures light didn't really stand up to the first experiment a couple hundred years ago, right? And why did they care about that? There's really good reasons. Medical doctors of the age wanted more data. He's hardly the only person of the age that was very concerned. There's the doctors that were concerned about washing your hands because they were showing it was killing pregnant women. There's all sorts of horrible, horrible things that actually happened during the period, in part because there wasn't a lot of science going on in terms of our medical practices of that age. And of course, this led to things like human death and suffering and money going to the wrong treatments and fraud being sort of propagated as a methodology, even though it didn't work. Or at least belief in something incorrect, if not fraud. So interestingly, although this was 1834, medical practices today still have plenty of problems, as I imagine many of you probably know. But there are procedures now that are wildly, wildly beyond anything we see in a field like computer science to detect fraud, especially today, corporate fraud, because this has been a major issue for lots of reasons I won't have time to go into. But there's registration of experiments, there's replication standards some fields have, they're required by law in some cases, so it's very complicated and tricky, but fascinating. In any case, so while I'm starting with homeopathy, the reason for that is that even though this talks about programming languages, it turns out that there are some parallels between the evidentiary practices of the early 1800s in medicine to the evidentiary practices of computer science today, with notable exceptions. And we know that this matters. Programming languages are sort of foundational. They're not the only thing that matters. There's all sorts of conditions that are important, like your processes, those can matter. The technologies you're using, the IDEs that you're using can matter. There's all sorts of factors, and it's a very complicated space, just like it is in other fields. You know, it's not like medicine is simple, right? It's an extraordinarily complicated search space to try to navigate through. And these languages that we have, even though it's only one part of the problem, it is an important part of the problem for reasons I'm going to get to. So for example, one thing that you might think about right off is how much actually money do we pay software developers, right? So it's kind of a hard question to get at. There isn't data from every country. But if you just look at the US and you look at Bureau of Labor Statistics data, and then you look at software engineers and people that sort of support them, so you can't really know how many of them use languages and how many don't, but you can kind of get a sense of how much it is. And we peg that from BLS data about $330 billion. Right? So it's not like a small amount of money. It's very expensive to pay software engineers. And that makes sense. Software engineers are highly professional people. They do hard jobs. They work long hours. It's a tricky thing. It's important. And what that means, though, is that given the size of the industry, even a small difference in programming languages or productivity by any metric can have a big impact at scale, even if you only consider our country, not necessarily others. So let's look at a case study from Google on compiler errors, just to get a sense. So as you know, Google tracks everything, and one of those things in the subset of everything happens to be compiler errors of their employees. And if you look at that, they published a paper a few years ago on having tracked about 26.5 million compiler errors from software engineers using either C++ or Java, right? Now, if you look at the data, and we cut this up into various ways and make certain assumptions that I can get into later if you want, but it looks at Java developers had about 29.7% of the time they had compiler errors, right? And for C++, it was a little higher at 37.4%, right? Again, these are experienced software engineers working in the industry at a major tech company, right? Yeah?
What kind of errors are included in compiler errors?
These are errors where the compiler rejected it. And so they come in a variety of categories, and they tried to categorize them. If you look on the right on the graph, these are the kinds of categories that they gave. But as you can probably imagine, sometimes it's a little bit fuzzy if the compiler doesn't know exactly what the problem was. But you know, other is a pretty small category, and most of the time it was things like dependencies and type mismatch and stuff like that. Yeah?
So, I see this on the bottom, you say percent of an 8-hour workday.
Yeah.
But it looks like the percentage is summed to 100.
Oh, okay,
So,
okay.
I mean, developers certainly don't spend all of their 8-hour workday fixing compiler edges. Right?
No. That's the point. In fact, it comes out to be like 20 to 25 minutes or something of a day. So the point isn't so much that that's not 100% of their day. That's 100% of time, right? I think is what their graph means. So.
Okay.
So if we made an assumption that this was an 8-hour workday, which is probably not fair, right? Because people are going to vary and stuff like that. But if we made that assumption for the sake of argument, then we could, and we assume that Google's data is accurate and honest and all that kind of stuff as well, then this comes out to be about $5.9 billion for Java at scale and about 4.48 for C++, right? Now there's lots of assumptions there. We can't say that that happens at scale because we don't know. But nonetheless, at least at Google, it's enough of money during the day that it's a non-trivial amount of cash. Yeah?
Actually, it's just an argument, I would think, because you haven't said anything, or they didn't say anything about what actually is going to happen to that 25 minutes. Maybe the programmers just go home earlier every day. It doesn't necessarily translate into actual money and productivity.
I would agree with that. Yeah. We don't know that for sure. You're right.
The one section says percentage of build errors. It doesn't say anything about time.
Oh, I'm sorry. Yes, I apologize. Yes, this is, okay. So they broke it into two categories. One of the categories was time, and I gave you those numbers for just that piece. And then this is the percentage of build errors in terms of like, how many were they in these categories? Thank you, you're right. That's exactly what it's pointing out. Okay. In addition, as it turns out, besides industry, education in the United States at least, and not just the United States, but a bunch of countries, are investing quite a bit in computer science for K through 12. This isn't just industry, this isn't just government, it's a little bit of both. So if you look at expenditures from this report called the BNY Mellon report, it doesn't look like that much. It's like $12 or $13 million across the states over the last 2 years. Not exactly a lot of cash. Even the amount that Microsoft, I don't remember the exact numbers, has given to code.org significantly dwarfs this overall for all 50 states. New York City gave $80 million over a 10-year period, and the Obama administration before it left pegged it, if I recall, around $4 billion is what is necessary to really do it. Right now, does that mean that that will happen? I don't know. But the point is that there's quite a few government and industry groups interested in having computer science lower, in part because BLS data suggests that industry needs more software engineers. Right? It's a major problem that you can look up very easily for that sort of stuff. However, the thing is that's funny is that in order to teach computer science at that level, you have to teach it in something, right? So it has to be in a programming language, unless you simply choose to do all like, you know, hand gestures or something, right? Or just conceptually, you could do that. And it turns out there's two major initiatives. One of them is called Exploring Computer Science. This is an approach that was put out originally by Jane Margolis out of UCLA. And it's a very specific curriculum that has made specific choices about what you do in the classroom. And it happens to be polyglot. So it uses 7 programming languages so long as you define programming language a little more broadly than Turing complete. So if you count HTML as a language, then that would be a language. If you don't, then it would be a handful, right? The point is, it's high school curriculum that uses 7 programming languages for whatever reason. I'm not defending or refuting the decision. I'm saying that's a fact, right? And one research team in the United States picks it for the whole United States. Like that's how that works. The second option that some schools are doing that's sort of up-and-coming options is called computer science principles. And so in this particular case, students basically take a test, and if they do well, they can get a little bit of college credit for it. No one knows what college credit, but it exists. This is programming language neutral, which has the opposite problem. Since there's no one choice for language, or even 7 choices, that means individual curriculum designers make their own thing, and as such, a student in Alabama might have a different conception of what a loop is than someone in Washington. Now again, I'm not saying that's good or bad, I'm saying that that's true, right? And these standards are very different. They're ratified by the College Board, so they've been vetted by a great number of computer scientists over a many-year period, and they're pretty sensible. I mean, like they say, you should understand iteration, you should understand, you know, conditionals, whatever. And if you look in college, there's also no real consistent sort of guidelines or standards. So A few years back, we did an analysis of just 39 colleges in the Midwest. And between them, they use C, C++, Alice, VB, Python, Java, C#, COBOL, and Ada. And if you talk to these individuals, actually, there's...
What is the name of a university that uses COBOL?
You'd be surprised. There's a whole bunch of universities that use COBOL, and it's for a really good reason. And one of them is because during Y2K, they found that you were statistically likely, on average, if you took a class on COBOL during that period, you on average got $10,000 more on hire than you would otherwise. So as a university, it made a lot of sense in that period to do that because of legacy code. So I completely agree, it's insane, but on the other hand,
The year 2000 only comes around once, right?
well, we'll get to that, so. Yeah, I know.
No,
They still use COBOL.
Yeah, but in any case, I'm absolutely not defending the use of COBOL. I'm just saying that when you go talk to people that use particular languages, they sort of fell into camps. Like one group of people would say, I use it because that's what I'm told to use, right? And then other people would say, I very strongly believe that this is the right choice. Like the individual, whoever it may be, that used Ada, I think there was only one school, really believed in that particular approach. Now, maybe he's right or she's right, but the data doesn't seem clear to me. So, and as it happens, these tools, they are dispersed. They have dispersion of designs, right? And it could be that this doesn't matter, or it could be that it does. But so, for example, one language might say, for left paren int I equals 0, 1, 1 minus 10, 1 less than or equal to 10, semicolon, I plus plus right paren left brace, system.out.println left paren double quote hello minus double quote plus I right paren semicolon right brace, rolls off the tongue. And another might say stuff like repeat 10 times, output hello, stuff like that. I'm leaving stuff out, but you get the idea.
So say even for trivial choices, actually, isn't it just, it does show dispersion for trivial choices, but those languages actually don't have a lot of dispersion for concepts. It wasn't like you were saying Lisp and ML and Pascal or something.
Yeah, I think that's actually true. So a lot of languages, they don't show dispersion for what their goals are or what they're trying to achieve. They show dispersion in the actual design to achieve it. Yeah, that's a good point. It's totally true. Yeah. And here's a good example. So generally speaking, most languages have this concept of string concatenation, right? Being Microsoft, I'm going to go on a limb and say I don't have to explain that concept. And if you look at the top example, which happens to be Java, then this concatenates. If you look at the example in the middle, it happens to not, right? Now, does it matter either way what the choice is? Maybe, maybe not. You could debate it. But at the end of the day, there's dispersion, and in that context, that means that the design leads to a different conclusion, right? It doesn't do the same thing, despite the fact that we could agree or disagree on whether string concatenation should be allowed on a plus. In other words, as computer scientists, we don't have much agreement on even very trivial things, very trivial things. And you might think that this doesn't matter, but in fact, some types of technologies, the dispersion gets a little wackier. So a good example is the web. When the web was being developed, it started with things like the HTTP protocol and HTML and these sort of technologies. And over time, we had different needs. We needed to run it on a server all of a sudden and have taken logins. And we wanted to manage formatting in an easier way. So we started making CSS. And then someone was like, well, I don't like CSS. I need less or Sass or these other technologies. And they're different. They're not compatible necessarily, right? TypeScript, Dart, you name it, right? On the server side, it's the same situation. There's a great deal of technologies, and they do very similar or the same things, but they do it in a different way. There's dispersion. That's what I mean by that. And the same on the database. There's many variants of SQL, NoSQL, stuff like that. Again, this isn't good or bad necessarily without evidence to support it. It's just true, right? It's that this dispersion exists, right? And this has side effects potentially, and they work in different ways. So let's take this Y2K example, which I happen to have prepared ahead of time. And as it turns out, during the late 1990s, it's very difficult to get good data on how much it costs to fix Y2K. We've looked at a lot of sources on this. The best estimates we've seen so far seem to peg it between 300 and 800 billion for the United States. But we don't know for sure how much it cost. And if nothing else, it seems like it's expensive. Some countries track it better than others. Some countries have their own estimates and they have some evidence to support them, but it's tricky to find out exactly. But nonetheless, it appears to have been an expensive fix, right? And Y2K only comes around once, but the problem is, as we progress as a discipline over the next 40 or 50 years, it's not like maintenance goes away. So today, you might write your web page with PHP and HTML and CSS and SQL and whatever, right? But in 40 years, it could be that someone has to maintain some of that code. Some of it will die, and some of it will need to be maintained. So the question is, which languages will live and die? What is the evidence for or against them? And what's the cost of maintaining a site built with N programming languages?
But, English, Middle English, Chaucer, stuff like that, you have the same kinds of problems. You have to learn a whole bunch of new stuff to read Chaucer because it's not written.
That's right. And so the question is, what's that cost? Right, that's the question, longitudinally.
What's the cost if you end up with things being static? In fact, there's actual benefit from things changing in terms of the adaptivity of language environments, what people are trying to solve in those problems. So just curious for you to factor the benefit, not just the cost of the change.
Yeah, I don't think we disagree. I think that this is a cost benefit. That's exactly right. But my point is that we don't have a good estimate of what those are, right? So I don't think we disagree at all. So
do you think this sort of agile DevOps movement in web maintenance, where things are changing in a very fluid and constant fashion, has an impact on the issue of long-term survival and maintenance?
I don't know. It sounds plausible, but I'm not sure. I don't know of any direct evidence for or against the hypothesis. So, and there's one last issue I want to mention with dispersion that I think people don't think about that much, and that is accessibility technologies. And when you look at undergraduates in STEM, about 11% of students have documented disabilities. This is a huge range, right? Like people on the autism spectrum, blind people, deaf people, you name it, right? And as it happens, some of these technologies have real problems because of dispersion, and they're well known in the accessibility community. So a good example is blind accessible technologies. If you want to make your technology blind accessible and you're using specifically Microsoft products, you're in good shape because you guys actually did a great job. And that is, you made iAccessible 2, which ended up being a standard in certain ways in other platforms, has all sorts of good properties, et cetera, et cetera. However, if you want your application to work on phones and Mac and all sorts of stuff, there are different technologies you have to code for. They work differently, and sometimes they don't work at all. So for example, if you have Oracle's accessibility technology behind the scenes, it is mostly incompatible for screen reading technologies. It's okay, it works sometimes, but not very well. So it's tricky. The point is that dispersion isn't just my plus operator is different. It's that since there's both a dispersion of the technologies and a dispersion of the implementations, what you end up with is inconsistency for different kinds of people, like the blind, right? That's the idea. But the problem is, this is one of those nasty problems that we've talked about for a long time in computer science. I'm not really telling you something you don't know, necessarily. We all know we have different programming languages, that we have to pay developers money. That's clear. And this is also one of those problems where one individual scholar or industry professional or even CEO probably can't fix it on their own. It's probably not possible. So the question is, were there other fields in science that had big problems, and what did they do to try to actually make progress on problems that were bigger than themselves? Right? How did we do that? And it turns out one of the most common ways was, number one, getting more evidence and trying to hammer it down very quantitatively. In addition, in some fields, but not others, there were also political movements. So we'll talk about that a bit. So one interesting thing written by a paper by you two, actually. Oh, you wrote this too? You're Devin Boo?
Yeah.
Oh, great. I love this paper. So yeah. That's true. I do really like this paper. So these three guys right here happen to wrote this really fantastic paper out of, I think it was ICSI, right? But yes. And they found something I found really compelling. I know the idea you guys would be here, so I didn't plant this, I promise. But
it's okay if you did.
It's okay if I did. Okay, great. Well, the point is, what they did is they basically tried to figure out what caused developers to believe things, right? What did they believe? And they categorized it in a whole bunch of different ways, and they found, and this relates to previous social science research, also something I really appreciated about the paper, that things like personal experience tend to be a little bit more convincing to people than research papers, right? And so things like what I hear from my colleagues or peers or managers were a little bit ahead of research papers. And there's a couple ways you can interpret this. And you guys were really cautious in your paper, and I will be a little bit less cautious, right? One way that you can interpret this is that social theory seems to indicate, as far as I can tell, that personal relationships matter, and that's probably true. I don't really have any objections to that. However, we might want to ask, what is in these research papers, and what is the evidence standard for these things, right? It's at least a question we can ask. And we might ask this because when we look at people like language designers, they make a ton of testable claims, right? So for example, it's a little hard to see, but you might believe that Ruby is a dynamic open source programming language that focuses on simplicity and productivity, right? That's what they say. I'm not saying it's true or false. Akka is a library, not a language, but you can build powerful, concurrent, and distributed applications more easily, right? More easily is a testable claim. You have to define it, but it is something that could be false and it could be true. Perl is flexible and powerful. Cue for laughter. And the point is not so much that language designers are right or wrong, it's that people clearly have beliefs, and there's also marketing claims, right? So it's a complicated situation. Of course, there's no problem with saying, I want to get my tools out there and get them used. That's totally normal. That's not a big deal. But on the other hand, that's the job of the business community. The job of the scholarly community is to figure out what's true, right? To figure out if something is true or false. Right? My job, I don't care about marketing. I'm an academic. So my job's a little different. And as it turns out, in addition to the research papers, developers are somewhat skeptical of research papers, or at least it appears so. It's my impression from the data, and you can disagree if I got that wrong. But I don't think you'd... Yeah, see, okay, there we go. So educators as well, people with direct expertise in computer science education actually don't understand the problems their students have. There's a wonderful, wonderful paper that was just published by Brown and Altadmri. He collected 100 million compiler errors. So I'm going to go out on a limb and say that's a sufficient sample size, right? And if you don't know any of Neil Brown's work, it's amazing. It's just absolutely fantastic, scholarly, tour de force type stuff. And one of the things he did in his recent paper was really made me laugh. He basically asked top conferences in computer science education like ICER, but also sort of like local UK teachers and SIGSEETs, sort of like a group of educators, but not necessarily experts. Like they might teach computer science or do other things. But in theory, they at least have some connection to students. But what he found is that you can look at the data and there are weak correlations, but they're very weak, right? Basically, if you actually track data and then you go ask experts what they think the answer is, they really have no idea, right? Or at least a very weak association with the truth, right? And this turns out there's at least some evidence. I think that this paper is far less compelling in terms of its size of its data, but nonetheless, it's an interesting paper, and I want to mention it. There's a lot of work that's gone in over the years on Unified Modeling Language, or UML. Just show of hands, how many people use UML in here every day? Yeah, this data, that's 0, just for all those watching on Ye Olde Internet. The data from Marion Petre also shows this. It basically says, we've spent a lot of time in academia talking about the details of these models and looking at them and thinking about them and making little theories about them and stuff like that, and nobody uses them, right? There are a handful of developers in her sample that did it a little, but generally speaking, developers don't use it that much. Right?
I think there's a sort of non-overlapping groups. I mean, so, IBM's Rational has a lot of customers, and they pretty push this approach that relies on UML. Presumably those people are quite happy with it.
Yeah, you and I are in total agreement. I mean, like, that's why I said, this is a sample size of 50 people that Marion Petre went and asked. Are those the right 50 people? I have no idea. But nonetheless, I think it's at least a data point to consider, even if I don't have a better sample. But yeah, you're completely right. That's totally true. Probably depends on context and organization, stuff like that, yeah. So, okay, then we can ask the question is what is actually in the research papers? Is there data in them, right? That's a simple and reasonable question. Did scholars, people paid to find the truth, use the scientific method and evidence? And it turns out, for programming language data, a few years ago, we ran a paper, and we looked at workshops. So these are venues that are not considered prestigious, right? They're not the top venues. They're just like some places that claim that they gather data on these issues. There's 3 of them. One was called Empirical Studies on Programmers. That no longer exists. There's another one called PPIG. It's out of the UK. A lot of Cambridge people were doing it for a long time. And there's another one called Plateau, which I actually participate in and I like, but nonetheless, it's reasonable to ask what the evidence standard is at such a venue. And it turns out, if you track the data very carefully, generally speaking, there wasn't really much evidence. And when I say very much, if you read the details of this, you find that it's astonishingly low. Like even simple things like, did they try to detect fraud, would not be included in studies on that. Now, I thought I was crazy when we found this, because we ended up tracking a lot more papers than was in this. We ended up with about a data set of about 2,200 papers. And we thought we were crazy, because a lot of the papers that were published at major venues, small venues, venues dedicated to certain tasks weren't really using evidence. And so I thought that was insane until this dissertation came out by a guy named Antijahani Kajanaho. Now, let me set the stage for a second. In the medical sciences, which is very different than computer science, between 1960 and 2000, the use of these sort of fraud prevention procedures, which were developed for good reason, increased past 1960 by 11.2% a year after this guy named Bradford Hill came into play. We won't go into the details, although they are insanely fascinating. He's the guy that figured out that smoking causes lung cancer, if you don't know, Bradford Hill. Increases it by 2,500% if you smoke a couple a day. Anyway, the point is, compared to those procedures, they ended up with something like 110,000 studies or somewhere in that ballpark. By the end of 2012, we had 22, right? So this includes top venues, Popple, UPSLA, major academic venues that are dedicated to programming languages, software engineering, any topic that you would think might be relevant when we're talking about wages in the size of $330 billion in the United States, right? 22 experiments. Now, when I say 22 experiments, I mean something specific. This is what Kajanaho considered to be randomized controlled trials. And that matters because these are fraud prevention procedures. These are like, you didn't try to cheat, like you had a control group. Like if you said Ruby was good, you compared it to something, right? And you didn't test yourself, just really, really basic stuff. Now, you might think this doesn't matter until you start looking at some other data from Andy Ko, who's at the University of Washington, if you don't know him. They analyzed 4 major top conferences or journals in software engineering, and they found something also sort of odd. On the one hand, they did find that 77% of papers do include some kind of empirical evaluation, right? So people are using some kind of data of some kind. However, even though it's software engineering, and in theory that's connected to like something related to people building software, only 27% evaluated human use of a tool. And of those, 62% of them tested themselves, right? They said, I have this great tool, I tested it on me, and it was kick-ass, right? That sort of idea. Now, this isn't my data. This is something I've confirmed with Andy because I didn't really believe it, right? That's insane. There's no way that should be true. There's no way that should make it past peer review. But 62% of the time, that's what happens. Yeah?
These numbers look like a CAG.
I have no idea. It's never been tested. But I bet it'd be better. But I don't know.
The culture is to use human studies and more, I guess, methodology that comes from psychology than we do in software engineering.
Yeah, I would bet that that'd be true as well, but I've never seen like a meta-analysis on it. So,
are you going to take a position on natural experiments? Do you have a feeling about natural experiments with reports or not?
Yeah, sure.
Basically, what we do with GitHub, for example.
I'm happy to talk about that, and I know you're an MSR guy type, that kind of stuff too. I love them. I think they're great. I actually use your research in my lab for generics because it does. Actually, it turns out. Okay, so let me explain this in the context of medical history. So in the 1940s, this isn't on the slides, but I know this off the top of my head because this is what I like. This is what I love. In the 1940s, there was when people were coming back from World War II, there was this huge opportunity in the medical community because soldiers were coming back and they had very serious problems. These problems were really serious to the point where the nation got together and said, we have to make sure we're doing for the best we can for the soldiers as possible. And the only way they could get the kind of sample sizes that people believed was through the VA. But there was a problem. It turns out the actual modern way of conducting randomized controlled trials was only finished in 1935 with Ronald Fisher's famous book on experimental design, which discussed like p-values and all that kind of stuff. And we all know that there's problems here and there with that stuff. But nonetheless, in the 40s, what was happening is the VA started doing sort of experiments and they couldn't really do it at scale, right? Like they'd go to this one hospital and the doctor would be like, I don't believe in control groups, sorry. And then you go to this other hospital and they'd be like, yeah, I'm not gonna use that methodology, sorry. And there was other people by about 10, 15 years later that started doing very similar to the natural experiments you're talking about, like on GitHub and stuff. The evidence center was much worse because they can't pull down a repo from Git, right? That's a lot easier. But they were doing natural experiments, and at the time, these people hated each other. They were fighting. And they were fighting because the one group, the natural group, was like the epidemiologists, right? That's what they called themselves, to my knowledge. And then there was the other group, which was the we need to prevent fraud group. Both had totally legitimate concerns. And so what ended up happening is this guy, Austin Bradford Hill, said, why don't we just do both and see if they match, right? And so what happened was they came up with this concept called coherence. This is Bradford Hill's like big idea, like fundamentally changed the world. And I don't mean that like in a little way, it really did. And it led to what is now known as the phase randomized controlled trial medicine. And eventually something called consort, which is an evidence standard to show replication of studies and to diminish corporate fraud. So the idea was really simple. It's like if there's people gathering natural data, why would we possibly not want to take that into account? On the other hand, since we know that we can't control natural data, we should use experimentation at various scales, and the phased randomized controlled trial allows for small and big ones, to root out who the liars are, right? So it's a little bit of both. You use a combination of metrics and you check whether they agree or not. And it turns out Christian's data on generics matches what other scholars do in experimentation. You may not have known that, but it's true. It's true, so good job.
Can you send me those papers?
Yeah, sure, no problem.
Well, that's amazing.
Yeah.
So I'm having trouble being a developer. This is vicious with this, right? But
No, go ahead, please.
the comparison you're making to like medical studies and what's going on in computer science, it seems that there's two things that are really very different. One is the cost of doing medical stuff versus doing. It's not like you go find people who actually are productively doing something and totally change their lives in medicine. Hopefully not, right? They now have to take a different pill, a different treatment instead of the other ones. The actual incremental cost to them is actually very low. Whereas with programming, you can't learn, I believe, being skeptical of stuff, you can't learn something by some small experiment. I actually have to get over the whole hump of learning everything and becoming proficient and knowing how to do things and spend, weeks, months, or even longer perhaps getting proficient before I can actually understand whether I was really better off. So there are a lot of hurdles to doing it. And then the other one is fraud. The nature of fraud seems to be really different. Marketing guys are all saying all sorts of nonsense, of course, but there's a lot less. Fraud happens differently, I think, in the sense that I actually can evaluate whether or not I feel better off using something or believing something somebody told me and applying it. So it's a real democratic thing that takes place. Whereas with medicine, it's like I have no idea. Maybe it helps me, maybe it doesn't, but the doctor says it's statistics, that's all beyond me. Whereas in programming, each of us who actually tries to go some path can actually understand whether we think it works or not. So the ability to actually commit fraud against me is a lot harder because I figure out it's a fraud myself.
Okay, I actually really appreciate that question. I really mean that because I think that this is something that's really hard to understand. And that is that, when you're talking about people committing fraud against you, you're definitely, I assume, and correct me if I'm wrong, you're talking about technical things. Like if I tell you go use this algorithm, it totally works, you can try it, and if it's not true, you can test that. That's really easy, right?
If I use UML, everything will go better. I tried to make me use UML for 5 years. So for example,
I believe
It didn't go better.
no,
I'm not surprised by that one bit. But what I'm talking about is slightly different. We're talking about things that are kind of harder to determine for an individual. Like I would never tell you, go use UML, right? That would never be in my lexicon. But I do think that there are questions where you can look at this coherence aspect, where like, what do we see from natural experiments and what do we see from experiments that are done at smaller scale or at different levels of scale? And then we can ask, do they agree? And that was the key with Bradford Hill. It wasn't saying, we have to operationalize this and now this drug is approved or not. That's like a government thing. It was saying, if we collect any data that we can find from anyone under any possible set of conditions that we can, does it agree or not? That's the difference. So it's more like a questioning type of approach as opposed to like, you should go use ML, which I don't really believe in either. So does that make sense?
Yeah, I think so. You're saying that there's a lot of data out there, and how do we actually think and understand?
Yeah, or even when we go get new stuff, like does it agree or not? Like if Christian's data disagreed with these other experiments, it doesn't mean that one of them is necessarily right. It could be that they both screwed up their methodology in different ways, right? So
just to clarify, so you're saying that the kinds of biases that one might bring, in all honesty, to natural experiment data analysis is complementarily dealt with by the biases that might obtain in controlled experiment design. Sort of.
I think that was Bradford Hill's view.
Okay, interesting. Okay.
Yeah. Okay, so, but I want to end this talk by talking about specifically experiments. I think there's wonderful, wonderful stuff out there that is on the natural side. I just don't know it as well, right? I know some of it, but I know the experiment side better, and I want to give you a sense of what it shows, right? And again, I'm not telling you to go do this or that. I'm just telling you what does the data show, and on whom, right? So, number one, if we talk about students. Now, when I say this, I always like to talk about students and professionals. There's a really good reason for this. And that is because people program at different periods of their life. There are students in K through 12 that are learning programming in kindergarten. So it's completely reasonable to ask, how hard is it for a kindergartner? On the other hand, and this is something Andy said in one of his papers once, actually, and he said, but people in industry actually invent the technologies. That's obviously true, right? Like it seems like Microsoft builds tools that get used by people, and if we don't take them into account either, that seems spurious, right? Like why wouldn't we just take both into account? And then look at what the data says as a whole. Again, it's coherence, right? This idea. And so one of the things that we like to do when we do student studies is we like to sort of tease out what things might be impacting them positively or negative, either on average or for groups. And you'll see that grouping matters in this context. So one of the studies we did a few years ago was on language notation or syntax, right? Now when I say syntax, I use that term loosely because computer scientists often think about it like this is a parser, right? This is not what I mean. What I mean is that different programming languages have used different notations to mean different semantics. And those could be done in multiple ways. Does that matter? And it turns out one way that we did that is, at least at the time, I grabbed one particular language that we made with rolling dice, which we came up with because of looking at Benjamin Franklin's experiments from the late 1700s on mesmerism, which was just another fraud technique. And so what we did is I had my graduate students sit around and like use a random number generator and generate a programming language totally randomly. Like the symbols were like slash for this and plus for that, and it's just random symbols from the ASCII table, and you had to try to interpret that. And we did that because we were thinking that might give us a baseline for languages. Like it can't possibly be the case that languages aren't at least as easy to understand as one where we used a random number generator. So we called it a placebo language. Right? Now, is placebo the right word? You can debate it. In the literature in the late 1700s, they called them sham treatments. And so whether you call it placebo or a sham is relevant, but that's the idea. It's something we shouldn't see work, right? Or that you would expect people to do poorly. And not surprisingly, people do very poorly when they're just starting out with a language that is designed randomly. That's not that surprising. What was more surprising was that Perl and Java didn't do any better. And we know why. The reason why is because of specific word choices that we were able to pull out using a statistical procedure called token accuracy mapping. And it's really simple. It works like this. You basically take the examples that people gave you, and they have to be small, and there's some rules about it, and you have to use these particular techniques to evaluate it, and you have to check reliability between independent observers of these techniques and stuff like that, and that stuff has to be hammered out and correct to do it right. But if you do that, you can actually see the areas of a programming language that novices did or did not do correctly. And it turns out a lot of the things we take for granted, like for in a loop, mean nothing to novices. So for example, if you use the word repeat over for, it triples their accuracy on that token. Triple. If you use equals instead of double equals and you overload it for both assignment and equality, which you think might be bad, I thought was bad. But it turns out it has no impact on assignment, and it gives you an increase on the equality symbol above 8-fold in accuracy. And when you think about it, that kind of makes sense. It's misleading, right, to a novice that hasn't already been trained. Right? Now, you might also think, this is a small study. This study was replicated, I don't know, a bunch of times, and then we ended up publishing 2 of those replications. One of them was small scale with 18 people. The other had 60-something, right? Same answer for both, right? Different samples, all that stuff. But you might think if we did a natural experiment, like we look at Neil Brown's data, maybe we don't get the same answer, but we do. In fact, it turns out the regions token accuracy mapping predicts would be hard for novices are exactly the same things we find in these massive natural data sets. We get the same answer. But, and this is an important but, this is novices, right? This doesn't mean this will help you, right? Not necessarily. So what we need to do is we need to also ask questions that look at different kinds of people. So one of the ones that we've kind of had fun getting hate mail about is the static versus dynamic typing debate, right? How many people have heard of this debate, right? You don't have to take a stand. I'll give you 3 possible positions. Position 1 is I believe static. Position 2 is I believe dynamic. And position 3 is either I don't know or maybe somewhere in between. So anyone for static? Anyone for dynamic? And anyone that wants to be on the fence? Okay, good. So as it turns out, this is 2 particular papers, and I'm going to show you a synopsis of a bunch more. One is from ICSI. If you look on this particular graph, it's kind of hard to see. These are box plots. I don't really want to explain all the details. But at the end of the day, static typing allowed these individuals to write correct programs defined operationally by the paper more quickly, right? And we know why. And the reason why is because if developers have dynamic typing, what they do when they want to use a function is they go look for what they pass to the function. And if you videotape them and you take out that time, it matches. In other words, if you have dynamic typing and you want to use a function, you have to know what to pass to it. And we thought maybe we could throw that effect away if we just put in the documentation what you pass to it. Turns out that doesn't work. Why? I don't know, but that's the answer. And then when you look at these things, one thing that people are often concerned about with experiments is replication, and for good reason. Because replication is hard, and unfortunately as well, other disciplines have things called evidence standards, and this is a technical term. This is not like something I'm making up. Evidence standard is a formal document adopted by a community that says you must follow these particular standards. A good example would be if you have statistics, you must report the p-value and the effect size would be a common example, right? And it just says you don't get published unless you have that, right? Or another one might be you must have a control group, right? Just something very simple. You can decide as a community for this particular venue or this journal, if you don't at least have this fraud prevention procedure in place, you won't get published. The most common one in medicine is called consort, and this one was designed in part because of all sorts of problems in the 60s, but also because of some famous court cases in the early 2000s where corporations were committing fraud that was murdering people, right? Which is not pleasant to say, but it's true. So they have this thing called registered randomized controlled trials. It's a fraud prevention technique, et cetera, et cetera. So we try, even though I work in a discipline that has no evidence standards for these things, I have evidence standards. And so one thing that we do is we replicate our experiments in all sorts of different ways. So for example, are statically typed APIs faster used? This is 2 studies mentioned at the top. The answer was yes. They had the same effect size, effectively. Same answer, different people. Sometimes different countries, right? Is the previous finding only a matter of syntax? Turns out if you twiddle with the type declarations to make them wrong, then yes, it's misleading, and that's what happens, right? Can documentation compensate for the positive effect of static types? Turns out the answer is no. It has a small impact, but the effect size is only 0.14. It's not that big of a difference. Do generics help with static typing? Turns out yes, but only in certain regions of the code, right? So it turns out if you have generics on method declarations, that tends to help. But if you have to use and write your own generics classes, that gets nasty, right? What about IDEs? So some of the previous studies were done in text editors only. It could be that just doing it in a text editor is the problem. And if you just had really good IDE support, that would help. Turns out it doesn't. Same effect size regardless of having a really up-to-date IDE. What about a benefit for dynamic type systems if you just go totally nuts and you try to design static typing where it's insane? You know, like you just come up with the craziest like examples where you have to have triply nested generics with question mark extends or some other nasty stuff. It turns out if you do that, there is a way to see a small benefit from dynamic typing, but it's so esoteric that it's hard to see most developers actually doing that in practice, although you could verify that with a natural experiment, right? In fact, you did, which is why we did it that way, right? And then finally, this one isn't published yet, but some people argue if only we had type inference, right? A lot of work has gone at like Popl and places like that to do type inferred type systems. It could be that that inference is what helps, but remember the theory here. The theory is that if you don't know what to pass, that's the cause of the time. So we would expect to see no effect, and we don't. Same answer, right? So we're talking maybe 10 to 15 replications. I forget how many off the top of my head now. And that data seems to match with people doing natural experiments, right? So it's not perfect, but that's where it is. So 2 other examples, just to give you a taste, right? One is, how many people have heard of aspect-oriented programming, right? How many believe it's helpful? How many believe it's not? And how many believe that it's either unclear or you're not sure? Okay, so there isn't a lot of data. There's only a handful of experiments, but they seem to show it has no impact. Like the types of things, the guy that made it, well, there's a few people and they argue about it, but one of the people that did it was Gregor Gonzalez back in the day, and they made arguments saying basically that it would help for certain kinds of code like logging and stuff like that. And you can find some effects for logging that are kind of small, but almost nothing else, right? So it could be that it's great for logging, but it just really isn't useful otherwise.
That seems to be the only
Argument I've ever heard for aspect-oriented is logging.
And in fact, the data shows it's the only one they've been able to document is true. And the effect size is small for that effect as well. I forget which task it was in here, but it's one of these. There's a teeny, teeny, tiny effect, and then the rest is just in a wash. So your hunch is what's supported by the data as well. So in any case, not much in the way of replications for that experiment, but you could try to invalidate them through natural or experimentation through coherence. And the final one is one that one of my students did. I just think it was fun. We have heard for years that lambdas were like the best thing in the world from many people. And so we were curious, right? So we decided to test just one thing, because you can only test one thing at a time. There's no replications on this to my knowledge. And I don't know of any natural experiments. Maybe they're there, or maybe there's some pieces in a couple papers here and there. But like I said, it's not as much my area of expertise. And so what we did was we thought, OK, maybe this is different across experience levels. Maybe you have to be really, really experienced with lambdas to use them correctly. Or maybe it's the case that it'll be the same. You'll get this big effect across the board. We weren't sure. So we tested freshmen in college, sophomores in college, juniors in college, and seniors in college. They learned lambdas somewhere around their junior year or so they would have known something about them. And for the professionals that we used, we got people that were like serious devs that knew something about functional programming. They were self-proclaimed experts in functional programming. They know what lambdas are. So there's no debate, right? But when you break down the data, there was no impact for the professionals. They could solve the tasks about the same amount of speed as using an iterator in C++. Right? This is just, again, one language. I'm not saying C++ has the best lambdas. I think they're kind of atrocious, but that's not the point. Well, no, that's not fair. They're not atrocious. They have particular syntactic properties that I think could be improved. There, how's that? Well, it's true. I mean, like, language design is hard, and sometimes when you're trying to be general, sometimes it's easy to get too general or not general enough, and that's a difficult problem.
given the thing you just made, how do you draw
Conclusions about lambdas from what you did versus lambdas in C++.
Okay. That's a great question. And the answer is you can't, right? So This particular test only compared two things, and that's C++ lambdas and C++ iterators. So we can't necessarily say that this would be true in Java, other languages, and some languages have very different ways of handling lambdas. And in fact, they use them in different contexts, right? So like, for example, the one area that if I was to guess where lambdas could be really helpful, there's some really neat stuff they do with lambdas in the JDK for concurrency. I have no idea if this would validate in an experiment or not, but it wouldn't surprise me if there was a benefit there. That could be documented, possibly. But I could be wrong. I don't really know, because we haven't tested that particular thing. But in comparing C++ to lambdas versus iterators, we found a very, very strong negative impact for people with less experience compared to doing a similar thing with iterators. And for professionals, we found no positive impact, right? Again, it doesn't mean you should or shouldn't use lambdas. It has nothing to do with that. What it means is that there was a technical team of people that spent years and years developing a spec and nobody did a test. Like maybe it's a syntax problem and they should have checked that. Or maybe like lambdas really don't have a benefit. That could be the case, right? At least in one particular language. But these were added all over, Java, C++, whatever.
Just in terms of methodology for people who are developers, people think they have
Some idea, the idea is to make the world better, okay? And before they can really know what it does, because novices just don't count for that much. In the big scheme of things, they don't cost you $300 billion.
Right.
You have to actually do it, put it in a language, develop a whole body of professionals who are expert in using it, and then actually measure it. And by that point, everybody's pretty much moved on, except for the guys who are kind of stuck in a belief system where they believe it's part of their world. So I don't know what you'd be advocating practically for applying what you're saying.
Sure, I'm happy to answer that, actually. So what I'm advocating for specifically, I don't have like a plan for action in the slides because I'm not trying to necessarily convince you to go do something. But what I would say is that other scientific disciplines break down big problems into manageable chunks, right? So for example, in medicine, we have early experiments, which are either phase 1 or before that, where they're really, really tightly controlled and they try to come up with a theory why something could be true. But we all know that just because you kill a bacteria in the lab doesn't mean that you're not going to kill the person using it. We all know that, right? Well, you would agree, right? And with computer science, it needs, I think, that one path forward would be to do something similar. So like, for example, if you want to change C++ for the whole world, that could impact a lot of developers, then there's a process. You have to have some low-level experiments that at least show it's plausible. And then if those work out, we need some natural experiments, and we need some experiments over here. And then if you go through this chain, then we say, okay, the evidence is sufficient, put it in C++. But it seems right now that the process is just kind of like people decide, and they might not do a good job.
I don't disagree with much of what you said, other than I'm not sure there's any hope. But more than that, one thing that does seem like there might be some hope here is if ignoring programming languages and stuff like that for a minute, so I think that's far less impactful than features in programs. So when people develop programs, they put features in. Excuse me. Like my favorite feature, not like, is the ribbon in Office. And I wonder, did that really improve the productivity of people who are using Office or not, and all the arguments and details. And so it makes me wonder if you could actually practically apply this in teaching a software engineering course that basically said, here's a methodology you can use when you put features into a program you're developing for users, that would actually let you know whether or not those features were a benefit to them or not. Could you do something like that?
Yeah, in terms of features, I don't think we have any disagreement there as well. And I actually do teach stuff like this in my classes as well for reasons like that. Like, for example, in software engineering, I'm not talking about programming languages, but I do want them to at least understand evidence for or against procedures. Yeah.
A world where people develop applications people use and actually understand these kinds of things and actually develop things that actually will be valuable.
Yeah, there's some speculation, and I don't know if it's true, but it would not surprise me. Oftentimes in university education for computer science, I hypothesize, but do not claim to be correct, that one of the reasons why we've done such a poor job, and we have really done a terrible job on using data and evidence for many things, is because we don't really require any education on it, right? Like if you work in some scientific disciplines, you have lab hours, right? And you have to run experiments on stuff. And we do that with programming. Like, we're pretty good, I think, as a community of trying to make something work, hacking it together and testing it, running the debugger, whatever your methodology is. But when it comes to knowing these sort of bigger problems that actually do impact a lot of, our productivity, that impact, the tools we use, not just the languages, but the tools and our processes and all these things, less so, right? Yeah. In any case, language is obviously complicated. Like I said, this problem is much bigger than me. It's much bigger than all of us. It's much bigger than one company. It's a hard problem, right? There's a reason it's persisted for a long time. But it also hasn't been studied very carefully. Like, there's not much data, as I think is clear from the evidence. There are some papers here and there that are making some progress or trying to, and we're trying to start a community of people that are doing this. So, for example, we have a Schloss Dagstuhl next year, which I'm sure a name I'm butchering, which is basically a group of academics coming together to try to say we need to make some progress, and it needs to actually use the scientific method. So, in any case, thanks for listening, and I very much appreciate all your questions.
Hey, just one comment. So so I think that the issue here is I think is a cultural one. Programming languages people view programming as a mathematical task, like proving, right? So if you're trying to prove something, what really matters is your notation and your definitions and your rules of inference, things like that. And whether or not these notations are accessible to hundreds of people and thousands of people and whether they find them appealing is irrelevant, right? And those of us who do empirical work, I think our software engineering side, we're sort of viewing programming as a human behavior to be studied as a human behavior using experimental methods. So I think these two disciplines have very different perspectives. Programming language designers don't, okay, I mean, I'm generalizing a bit here. So people who design languages like Python have a very different perspective. But if you're designing languages like Haskell or TypeScript and so on, you're coming from a very different perspective, which is what is the right notation? Does it have the right semantics? Can I prove the right properties?
Yep. Yeah, that's true.
How humans like to use it is not really that relevant.
Yeah, and if no human ever used programming languages, I think that perspective would be valid, right? But you are right. That's absolutely what's going on. Is that these communities, they've existed for a long time, and they kind of have their thing. They do type soundness proofs, and they twiddle with some semantics and stuff. And there's nothing wrong with that. That's totally okay. That's fine.
Programmers in your dog stool.
Yeah, we have a diverse group. Let's just say that.
Do you have do you have empiricists there too?
Do we have?
Like, you have the PL side.
Oh yeah. For sure. We have people. Well, we're trying to get a lot of people outside of computer science as well. People that understand evidence standards and stuff like that. Well, I've tried to get one. I don't know if he'll go, but in any case, at least some people that do. There's other evidence. I'll get you in just a second. Sorry. There's other evidence standards besides the ones used in medicine. Evidence in medicine uses consort, which is by far the most rigorous of anything out there that I know of for empiricism. Because, if you don't do it right, you die, right? That's kind of a big deal. But other communities have been moving, either adopting consort wholesale, or they develop their own because of the law. So, for example, in education, they use the What Works clearinghouse. It's not as rigorous, but it has like fraud prevention standards and stuff like that. So I think he was first, and then yeah.
So I just really appreciate that point because something that's always been a mystery to me is having grown up in universities where I had lots of language designers and working with language designers and type safety debates. And this programming was, that's why I came to this, sort of lived through a lot of listening to programming wars. How come all the languages everybody actually uses that are really successful in terms of broad communities are horrible?
So actually, the only paper I know of that looked at the adoption in a really rigorous way that I would consider as scientific as we have right now is this wonderful, wonderful paper by Leo Marovich. It's this guy that graduated from Berkeley this paper, yeah. Graduated from Berkeley a bunch of years ago, and I forget the name of it, but it's like Empirical Studies on Language Adoption. So I'm happy to send it to you. No, that's the early one. The socio-PLT paper is fantastic, but the one that had the biggest dent, I think, was the Empirical Studies on Language Adoption or something like that. Socio-PLT tried to come up with a theory, and the other one was like what actually occurs, right? Yeah. But both are good, though. But like the socio-PLT paper had this fascinating observation that religious communities that are hard to get into, people tend to stick with them. This is what I was about to get to. It could be the case that that's part of it for languages, like if it's nasty or like I learned it, I am not doing anything else. But I don't think so. I think that his paper leans more toward that it's a social construct. Like if you work at a particular company that uses X, you tend to use it. If you work in, if you use a programming language, you tend to use the ones that you heard about before. So for example, if I recall correctly, and I'm not prepared to talk about this paper, but off the top of my head, I want to say that the strongest predictor of what language you'll use next is the one that you used previously. So, stuff like that.
Great theories, I guess, on the scientific side, but just observing this over my career, okay, COBOL became what it was, partly because RPG was really, really horrible, because businesses said this is what you did, just like you bought IBM, and because you could express big numbers in a world without a floating point, you could represent accurately with pennies. Okay, so there's some things that really compelled people for business reasons to do that. Okay, Pascal came along, and that was really successful because everybody was forced to learn it. It wasn't successful, but for a while it looked like it was successful. Everybody was forced to learn it by people that taught in computer science departments, which were all like new in the 80s. Visual Basic came along, and I remember making fun of a friend of mine who was looking for Visual Basic programmers because I was like, a C, C++, that kind of thing. And he says, oh, look, my experience, and again, it's his experience, is that he was able to get cheaper, more productive guys. He ran a consulting business who could actually produce code faster. And so they have an argument that people got into that. And then once they're in it, yes, they're used to it. They know the language. We tried to get them to go to C#, and they're like, what are you doing? We love Visual Basic. And then the web thing comes in. They're all different reasons, maybe, why people found something that became a great tool for what they had to do, and then the thing becomes entrenched. But I think the reasons actually are kind of varied, like I was trying to illustrate there about why it happens. So this thing you were saying about understanding kind of the human nature aspect of how humans interact with programming languages and environments is probably far more relevant from certain perspectives than all the analysis of types and what languages should look like and productivity and 10% improvement here. There's a social human factor that seems
I don't think necessarily that Marovich would disagree with that. Like these human constructs, that's what I'm saying, it's kind of a social problem, right? This is what I mean by that, is we're saying effectively the same thing in very different ways, but
Parts of the theory
you gave about communities and things like that, I think work for some languages, but I think there are a whole bunch of different reasons.
Yeah, I agree, and that's actually what the Marovich data paper shows, is that it's complicated, right? Adoption's a complicated thing, yeah.
So I wanted to ask kind of two questions that are related to each other, which is about how do you evolve? So the first question is about, let's say a language came out, there's like 15 studies that show that the use of angle brackets for generics turns out to be worse than if you use something else. How do you evolve that language given that it's already out there and there's code written in that language? And the second thing is, we have a community of researchers who apparently in software engineering don't often do randomized controlled trials. How do you evolve them to start doing that without saying, tomorrow the standard has changed and we're going to reject all papers that don't do these randomized controlled trials perfectly, which is the kind of thing that's actually happening with user studies in some of these fields, like in the ASE conference or in FSE, where it's not been common to do user studies. Now all of a sudden, people who are good at evaluating user studies are like, well, that's not done properly, so I'm going to reject the paper. So there's no way to teach the community how to do these things without making them perfect. Like, how do you evolve both the languages, the programs, and the people over time to get to better standards?
Boy, that's both of those questions are super hard. So thanks. Let me do the second one first, because I think that it's not necessarily easier from a social perspective, but I think that you're completely right. Like the implication of the question is that this is not Boolean, right? Not only is it not the case that all papers should be randomized controlled trials, that's weird, that there needs to be coherence. But in addition to that, even people's understanding isn't Boolean. Like we don't teach how to do this stuff in school, not really, at least in computer science. We don't really teach it at conferences. And you can't fly around to every conference and do like workshops and stuff. I know there's been some, and I've done some, but that's hard. So the question is, how do you do it? And the answer is, I don't know exactly. I think this is a problem that's bigger than me, right? But my suspicion is there's probably an educational component. We should try to get it into schools more over time. I think that we should try to get it into like conferences in terms of like workshops to help people. I think that would be good. I think that the National Science Foundation giving money to it, meaning like they should get communities together that are both scientists and practitioners. You know, like we need people that are in the trenches, not only to study, but to give feedback, but we also need people that understand all the data and stuff like that. In medicine, they took a totally different tact for changing it, and that is they changed the law, right? And specifically what happened was, in the 40s, doctors didn't want to use the scientific method, right? Because they believed they were right, and they were trying to help their patients, so Congress changed the law. And they started to say, this happened really early, actually, like, so in 1902, they changed the law so that if you were to give a drug, you had to say what was in it, right? And like that sounds today like totally obvious, but you had to say what was in it, but you didn't have to say whether it works, right? And then in 1927, they created the FDA, and they said, okay, well, we don't know what the answer is or how to evaluate it, but we do know that we should check if it kills people, and sometimes it was. So the question is then, how do we proceed? Do we get communities to have minimal policing and pop it up over time? Do we do training? Do we do all of the above? Since I'm kind of a coherence guy, I kind of take the all of the above approach, but I really don't like exactly what you just said, which is just like, oh, this is totally imperfect, we need to reject everything like that. I think that's nuts. I think this is learning, right? Researchers learn too, right? Maybe you disagree, but I doubt you do, but yeah. Okay, so then there's the first question, which is, what do we do about evolving the language? I think this is actually really hard. And so, you know, I like to solve really, really easy problems, right? Or try to. So there's been a number of approaches I think we all know. Some languages take the approach of, we're only going to add to the language, and we never change anything that came before it. And then there's the opposite, like the Python 3 to 2 debate. How many people know that? I don't. So it's kind of like they changed some stuff that broke backward compatibility. And so I'll tell you two things that we do in our lab, but we have it easy compared to all of you. In my lab, we developed a programming language called Quorum, which is only used by about 2,500 kids, but that's still a lot of kids, right, all over the world. And so we make a rule, we say we're going to break backwards compatibility once a year. And we can do that because it's mostly teachers and we work in education. The next generation of kids that comes around the next year does not care at all, right, because that's not the point. But that's not fair. That's not an easy thing. Like if you're working on C++, then you know, you can't just say, sorry, we don't have pointers anymore, because you're going to break a little code, right? I'm going to go on a limb, right? So the question is, how do we do that? I mean, I think, again, it's a multi-pronged thing. Like on the one hand, we have to get people to understand even what evidence is so that they think that maybe there's a need for that. We need to train people on what the impacts are and go for the biggest ones. But we also have to do it in such a way that we don't break the things that will cause the most harm to the community, like turning off pointers all of a sudden, stuff like that. All right, that's just an example, but you get the idea, right? Features that are fundamentally game-breaking. On the other hand, it could be that for some of these languages, over like a 20, 30, 50, or 100-year period, that we can start to change a few things here and a few things there on a schedule, where everybody knows it's coming, everybody knows what the plan is, and everybody knows what the evidence is and can try to refute it, right? They can say, C++ on this date is changing to this in all the compilers that people do. And if you don't like that, here's the study methodologies, the data for them. And if you don't like it, you can try to refute it. But, you know, this is Andy's pipe dream world where that. Really? Did they try that?
I don't know about that, but
Okay.
that's a great thing, because earlier you said Y2K only comes around however often, and you just came up with a way of having it happen every few years.
Well, I said,
Rules and all that existing code.
I don't know if that's quite fair, because Y2K was a problem that was deeply rooted. But like, suppose we said, you know, it depends on the amount of change that you're requesting, right?
But any change renders old code, perhaps.
Well, not any subtraction or change, right? So like an addition wouldn't.
Yeah, that's fair. So if you have some rules about that, but that would be the thing that worry me is that.
Yeah, so subtractions would need more evidence than additions. You know, you'd have to be sensible, right? So.
Does anyone in the room know how many versions of C++ implementations there are that do not parse by every compiler?
Yeah.
Like literally are hundreds, and that didn't involve that many official versions of C++. And yet there are still so many that can't read, like lots of code from Microsoft can't be read by non-Microsoft compilers.
Yes, that's true, but I discovered an interesting secret about the Visual Studio team. I used to be in Windows until very recently. And it was this, that I was doing something about who was checking into our tree and doing some stuff and, signing bugs and people automatically long ago. And I discovered that besides Dave Cutler, who changed everything, that there was this one guy who was checking in all these changes to virtually everything throughout the entire tree. Turned out to be the guy from Visual Studio whose job it was to make our code work with the latest compiler that we're about to drop.
Thanks. Yeah.
So I don't think there's, it's very agreeable and kind of obvious the way you've laid it out that we should have more controlled studies and better evidence for these things. But I wanted to ask the example in almost all of the running theme in all of your examples is this idea of productivity. And I'm wondering if that's like is that an innocent choice of metric? Like, why is that the thing that we're looking to optimize or study?
Oh, no, that's a great question, actually. So it's not the only thing that has been studied in the literature, but it's one that is often mentioned in terms of time because time costs. That's usually why people study it. Like, for example, if you know that you're going to reduce the time to fix compiler error. Here's an example. There's a natural study, not a controlled study, but it's a really excellent natural study by Brett Becker, this guy in the UK that is kind of a young dude that maybe isn't that well known yet, but should be because his work is fantastic. And Brett did this study on like changing compiler errors to be sort of like more friendly to people, right? And he did just really obvious things, like instead of saying like, eat my face, it would say, hey, there's an error on line 5. It's a terrible example. I don't know why I said that, but just bear with it. The point is, he would take messages that were perhaps esoteric and he would do his best, right? He didn't have a methodology for knowing what to change in them, but he wanted to try. And he found some percentage decrease in the amount of time to remove errors. Now, in that case, it's time, so you could call it productivity. But he was thinking that if that was a developer, that would cost, right? So that costs money. But on the other hand, like, that's obviously not the only thing you care about. You could analyze comprehension metrics, you could analyze accuracy. So sometimes we do accuracy studies for syntax, like how accurately can they put in the syntax, stuff like that. And I think all those things should be studied. Again, it's coherence, right? Like you want all these studies to know the totality of evidence. But time is a common theme for that reason, so yeah.
Well, there's a dominant thing that's changing
In producing software, which is not the time you spend developing the software, it's the time. It's always been maintenance and things like that. It seems to be a bigger cost factor probably.
Right, there's some evidence of that.
But now it's the vulnerabilities.
The what?
It's the vulnerabilities in software. Producing software with vulnerabilities, every day you read the paper, the tremendous cost to society and companies and everything else by vulnerabilities.
Oh yeah, that's a great idea. I've heard that before. I gave a talk at CMU once and someone mentioned that.
Yeah.
And I think it's spot on, right? Like, why not? Why not try to figure out, can we reduce that a little bit too? That's great, yeah. And this is what I love about this coherence idea is like, it doesn't say, this person's right, that person's wrong, whatever. It says like, why don't we just look at it all and then try to reverse engineer it? Natural studies are good, controlled studies have a different purpose, and they work at different scales for good reason, right? They let you try crazy things, right? Anyway, other questions? All right, well, thank you very much for coming. I appreciate it.